workshop. And it's a great pleasure to have Uwe Franke talking. He will give a presentation of 45 minutes. And so Uwe Franke is with Daimler Research for many, many years. Uwe, for how many years? It's there. 30 years. And yeah, so he's been pushing very hard all aspects of computer vision, autonomous driving on the more low-level depth flow, scene flow. He's doing a lot on 4D vision for a long period of time, and then obviously with neural networks, he's been pushing a lot the semantic segmentation and the Cityscape dataset. I guess we all know that. That has been a very great dataset pushing the field forward. So thank you.
Well, here it is. Welcome, everybody. Within the 30 years I've been working on computer vision with Daimler, I wrote many, many proposals. And one sentence was in common with, I guess, all proposals, and that is, let's make computer vision more robust. Never say, forget this word more, because you will not succeed. So make it more robust. In order to make it a little bit more challenging, we always edit and achieve real time. In my talk, I will go through 3 topics. First, let me quickly show you what we did in the pre-deep learning time, what we did there to make things robust, how the last 3 years changed everything, and what nevertheless bothers us today. So let's start with the old, ancient times. And in '96, I came to the conclusion that monocular vision, that time with a 300 megahertz Pentium, that will never work. So I looked for a second camera and started in '96 doing stereo vision. Well, that is what we achieved that time. Very simple operator running over both images. It was a census operator, we didn't know that time. 8-bit regularization, a little bit to have this ordering constraint in place, a density of 2% of the pixel, and it took 80 milliseconds to compute an image of 512 times 512. So that is everything but not robust. But if weather was overcast, it worked. A few years later, we found a nice, computers became more powerful. We find a nice way to do correlation very fast. So we had kind of correlation with a 9x7 cross correlation function. But you see all the problems that we had at that time. How does that works? No, sorry. We had this problems here with periodic structures. We had all the holes and errors here. So that was improved over time, but then in 2005 there was a wonderful poster at a German conference, it was in Vienna to be precise, by Heiko Hirschmüller. He introduced semi-global matching. By the way, it was not worth to become an oral because it was just semi-global, not real global optimization. So the reviewers decided it's not worth to present it in the auditorium. But you know that this in the next years became the basis for stereo vision. We use it now. We have a 63-bit census. Regularization is done by Heiko's famous algorithm. Density is over 90%, but that was very, very slow. In 2005, it took us 2 seconds per image, but we saw that it's a great thing. All the errors that we are used to disappeared. So we went to specialists in FPGA programming, and together we were able to realize that wonderful algorithm just 3 years later in real time. And I have here one of the very first videos that we took from a ride. Nowadays we know that this is standard. But then we drove into our garage and we were totally surprised by this image because there's a white wall. And I told my boss for years, it's impossible to measure the distance to a white wall with a stereo camera system. And now I had to learn that I was wrong. There's sufficient information, not for a correlation approach, but for a semi-global matching approach. We see here the same situation in 3D. This is the wall. It's noisy, but it's clear. Wall, that is the solution. Okay, we are used to that. That went into serial production. We will, you know, from the Daimler cars. But that was for us the standard algorithm there. We did many, many investigations and always found out under all aspects that that algorithm was significantly more robust than any correlation approach we had before. And there were challenges, and this is a robust vision challenge that we ran in 2012 at ECCV in Florence. There was given by Daniel Konderman, who is, I think, at the conference. He collected data at adverse weather conditions. And you see here, you see it snowing at dark, at nighttime, and so far. And this is the reconstruction of the best algorithm that time. And also, although it was 7 years later than the invention of semi-global matching, a special variant of that algorithm was still the leading algorithm, not to compare with that, but that we have seen tomorrow. Then there was a workshop in a German conference, GCPR, on unsolved problems, and I took some slides of my talk that time. Well, SGM, as we know, is great at good weather. I told the colleagues that time, oh, it's acceptable at night. It's a problem at a rainy day, and if it's dark additionally, then don't use it any longer. I have here an example. These are 5 consecutive frames of an image pairs taken under heavy rain, and below you see, all again in this color encoding, the disparity estimation. Red always here, these red dots that are very, very close obstacles, so they are just in front of your windscreen. And here the wiper covers the data. And what you also see, the blur is very different depending on whether the wiper was active just a frame before or not. And you see here, always the reconstruction. There's a car in front. It's nearly not visible. We have all the arrows here. And that goes on, and this is the problem. So we thought about ourselves, what can we do? And what the solution is that we say, okay, semi-global matching is doing spatial smoothness, and what we need in addition is temporal smoothness. So we invented a scheme that we named Temporal SGM. And so by now using all the correlations that we have and forcing smoothness in all 3 dimensions, we can do much better. You see on the right side the results where most of the errors are now no longer existing. So that was a step forward in robustness. And I have another video, a situation that again shows that the situation, now it's heavily snowing. That was the heaviest snowfall I ever had around my lab. And the reconstruction, of course, is extremely noisy here in this low or non-contrast area of the sky. And we see also, if we let it run, all that noise here on the street. And so this is not robust. And what does it mean? What does it mean if we have this noise here? If we have a look in 3D, you see all these obstacles here hanging in the sky. That is the sky, which is incorrectly correlated, and semi-global matching is not able to remove that noise. But if you do the temporal domain into account, then we get a clear response. Okay, parallel to that, we had a project where we wanted to derive a very compact representation, 3D representation of the scene. It led us to this pixel representation I'll show in a second. So we had that time 500,000 3D points, which we wanted to compress in, let's say, 1,000 objects, small sticks, rectangles, staying at a certain distance, approximating the world, having a height, and assuming that our scenes, we have obstacles that stay perpendicular on a flat or planar surface, so we enforce this, this configuration. And if we run the video, you see here the free space from geometry clearly separated, and the sticks, and if I remove the grayscale image, we still have a very good impression of the geometry of that scene. And that is a video from 2013 when we did autonomous driving, Bertha Benz drive from Mannheim to Pforzheim in Germany. Okay, the nice thing with this very compact representation which we derive for the communication with the fusion is that it is a strong regularizer. And we see it here. This is terrible image, heavy rain, and all these red areas here, and also this green one here, that are errors. And since semi-global matching has a smoothness constraint, the errors are correlated, and if we do nothing, then also we have here ghost objects. And that will cause a breaking, which is not intended to do. So what we did is we added confidence. We found a way to somehow estimate the confidence of our stereo depth estimation here. And if we put this, and black means inconfident, and white means confident, and you see this area here is black. And if we add that to the optimization in the Sticksel world, then we get rid of the phantoms. And I have two examples. This is at nighttime, it's in a tunnel, and you see the noise, and this is now absolutely clean here. And we have a video here. It looks pretty, but we have this reflection here, and causing strong errors in the disparity estimate, but now it's cleaned up here. Okay, everything is fine until you go to San Francisco. Now you have a flat, planar surface, and then you have these steep roads. And what happens is, if you do not do anything against that, that the geometry tells you there are obstacles, like a LiDAR does. So we had to find a way. We decided we need to find a way to come around that problem. And what humans do is they understand that that is road, so don't put an obstacles there. So consequence, we started a project on real-time pixel labeling. Handcrafted features based on RGB, based on depth, helped us to do scene labeling. We use the random decision forest classifier. We see here the street, the obstacles, we have vegetation, and in Kitty sometimes also sky. We turn, this is not sky, here's sky. So when we put that into the optimization to get rid of the errors, I will come back to that problem later. What also happens is, instead of saying, okay, this is all obstacle, this is all drivable space, we now, got the information. Okay, don't drive there. That are the trees. That is sky. We get a better segmentation of the bike and the car. Just adding semantics. And in order to bench this algorithm and its the next generations, we decided when we was in Münster a couple of years ago, 2014, let's collect data. Let's build a benchmark. So Marius, of course, everybody knows, went over the year, got a specialist in Germany, in German cities. He went to 50 different German cities. He collected all the data. You see here Aachen, Berlin, Frankfurt. And that was meant to judge, to benchmark the semantic labeling that we had at that time. But before I continue with Cityscapes, I would like to step a moment back. What did we learn in the past? Well, receptive fields, bigger is better. Matching, linear operators or these standard operators are good, non-linears are better. Regularization, spatial is good. if you take into account that the sequence is better. Smoothness is good, but we could prove that Stixel worked much better even than other superpixel approaches. Confidence measures, they should be available in all stages of the pipeline. So then you get good results. But we also learned, okay, and you know, stereo vision went into practice. We have now in nearly all Mercedes-Benz car lines a stereo camera system for emergency braking, for lane keeping, all the other stuff. But we also learned semantics will be the next step, and therefore we are here. Because now we are in a situation that in 3 years we are working on semantics to make our computer vision more powerful and also more robust. When LAMP came in 2015, just exactly 3 years ago, there was Boston, and we all learned from the Berkeley group that you can go from an image to such kind of segmentation by this well-known Longfellow-Hammer paper for fully convolutional networks. And in addition, strategy, we learned GoogleNet. They gave us a chance to make that fast. This was June. My people came back. They set up the whole pipeline. I went to holidays, to vacation. When I came back mid of August, they forced me to sit into the car. Who forced me is sitting there. David said, if you don't go with me in the car now, we are no longer friends. And what they showed me is this. These days, that is normal, but try to understand why it was so fascinating. There were dozens of PhD theses on occluded object recognition. Put them in the library. It's solved. We had pedestrians at 80 meters before we talked about 30 meters. We can decide between motorcycles and bicycles. I would not be able to design an algorithm that can do that. We have this clearly separation of sidewalk and street. We have grass. And believe me, of course, Stuttgart has never been in the training set. We didn't go to Stuttgart for that reason. Wonderful. Okay, that time, this was with 1 Hertz. Well, a little bit later, we were close to real time. And that changed everything, definitely. Okay, you know Cityscapes quite well, because I guess you are one of these nearly 9,000 people that downloaded Cityscapes dataset so far, starting in 2016. And maybe you also belong to the people here that submitted to the benchmark so far. And I would like to go a little bit into Cityscapes, because I can show you images that you can't see. And this is the curve that shows the performance over time. And you see that semantic segmentation very quickly went up, and now it seems that it's saturating somewhere here, while the instant segmentation benchmark, that is still alive, and there's much progress during the last years. Well, I selected this image just by chance, because it's so beautiful. It's Berlin, and I will show you results using that image. Here we have lots of pedestrians at that places. This here, and also in the back. And I also would like to draw your attention to this bus here, hidden by the trees and the poles. And also interesting is to have a look to these objects here, these concrete objects, which on the first glance look like poles. Okay, this is the ground truth. You see now the pedestrians, this here, 1, 2, 3, 4, a bike here, 5, 6, 7 places, and the back. And these are labeled as unknown, because the label didn't know what to do. Now we go through the contributions, some of the contributions by performance. We start with ZNet, and then 60%, 66%, 67%, 70%, 71, 71, again 71, 73, 81. This is the last where the paper is out. There are other contributions where we don't have the paper so far. So, and, sorry, some more. Now if we compare, because that was too fast, there's a 60%, there's 70%, there's 80%. We see here now the bus is visible. We even have one pedestrian here. And the small, what turns out is the small details. There are differences between 70 and 80%, but just for the small for this very small difference details. So from a feeling here, there's not a big difference between 70 and 80%, but very much against 60%. And we ask ourselves, where do the algorithms differ? And we have here the two leading algorithms this time, and we gave them this image of this castle, the ground truth. And what we see is, oh, they differ very much here in the trees. That is the better one. Here, there's a big difference, so this is correct. And there's also a big difference in the front area here, which is labeled as street, and comes here, and is here street, and here is the ground class, which is not street, but anything else which is on ground. So also this way. The other image that has significant difference, or many of we ordered them by difference, is shown here. This is the original. This is the labeled image, ground truth. And we see differences. This algorithm called this wall, or it has been labeled as building. And here it's saying wall, that's fine. The other, the opposite. It shows some problems because we have a labeling. I come to that point later. But if we go back and forth, we see, fortunately, the important things, car, pedestrian, rider, bike, and in the background, there the differences are small. Okay, I have a last slide on that. We asked ourselves, or Marius did that investigation in his PhD, if I take 10 of the best systems and look how often do they agree in their judgment, we see that 94% of all pixels are correctly labeled or classified by all the 10 systems that we run. But the rest of the 6%, we have 1.5% of the pixels where only one classifier disagreed, and more 2 disagreed, 3 disagreed. Here, that's interesting, they have 1.5% of all pixels where there were total disagreement by all the 10 experts. And the only explanation is that we have realizations, or we have things in the test data set they have never ever seen before. Okay, so far this short insight into Cityscapes. What do? We do not do semantic segmentation just for fun because it's giving these nice images. We do it in order to improve our representation of the world, which is the pixel approach. And now these days we have 2 million pixels in 3D. This is the pure depth. This is semantics. And then we fuse this information in some kind of optimal manner to get that representation where now each pixel also knows its label, its class it believes to, and it's enforced that every pixel has just one label. And if you go now to Stuttgart, we get this video. It's not as nice as the one before, but it's just 1,000 objects, 1,000 pixels. And now you can give that to Fusion guys, and they can do wonderful things with that because now it's really, really compact and noise-free. Since we have that in the car, we have never ever seen a ghost object in front of us any longer, except very, very extreme bad weather, when all the systems break down. And again, this situation, no, we add the semantics, and we get that. Yeah, we have a clear road here, we have a clear sidewalk, and if we look to the car, that was one obstacle before, and we look there, we see here the driver labeled as a pedestrian. Okay, let's have a look to the instance segmentation benchmark. I selected 4 different algorithms, just show you how the progress was over time. Well, the first one is the one Jonas submitted, just that we have a baseline for that. And we see here that some of the cars are fused, so it's not able to distinguish, to separate these cars here and here far away. All the cars that we have there have not been recognized. That is a year ago. Still missing all the cars here. That is mask RCNN, here at all at ICCV last November. Significantly better here in this area, and also these cars are separated. And that is the currently leading algorithm. And if I go back and forth, it's impressive. Okay, the colors are by chance, but it's impressive how far we got. The second example, here again, our old algorithm not able to recognize this big truck as one object because it was so big. The receptive field and everything was not large enough. This is last year. Have a look here. This belongs to the bridge. Keep that in mind. This is mask RCNN. And again, CVPR this year. This year, unfortunately, is wrong. Well, looking for small people, for small pedestrians, the algorithms now detect everything which is somehow look like a pedestrian or pedestrians. But this shows us a considerable progress in performance. And we are looking forward what is possible in instance segmentation in this field. Robustness means night, the bad weather. Let's have a look to night. We talked much about the night this morning. Okay, I took that image in Stuttgart, and then we ran our algorithms on that, and of course it's nothing. Yeah, it's bullshit what comes out. That's for sure. Other domain doesn't work, but we added just 10% of the data of night scenes, and then we get that result. Clearly separation between sidewalk and street. Even the sky is visible, or the cars, the truck is another color. Works pretty well. I give you a short moment to inspect this image you have never seen before. What is in this image? We see here the reflection. So yes, it's a sidewalk there. I guess you see the bike. Yeah, there's the bike, sidewalk, sky, and the pedestrian here stepping onto the road. Last example, I like very much. Reflections are everywhere, here and here, but still neural networks tells us sidewalk, street, of course, bike, rider, and pedestrians over here. So not too bad. And I love all the Judith Hoffmann presentation this morning, but just adding data seems to help also. But we have to learn in the future what is the best strategy to get other domains running. What did we learn? Semantics will be the next big step. We are right. That definitely happened. In 2013, we said it's all about features. We ever heard that sentence? But now it's all about data. Data sets and benchmarks push the world forward. So also challenges like this one, wonderful thing, very helpful. And deep learning paved the way towards level 4 to 5. That would never have been possible with the old algorithms. But we have learned that we have to somehow be able to measure robustness. And that is my last part. What bothers us today? Labels, scarcity, and more we will see. Labels, well, it's easy. It's not an easy job to label such an image. If you take an image from the highway, it's nothing, but this is not easy. Why? It starts with the problem we have maybe many classes And all the data sets come with different numbers of classes. So nobody really knows how many classes do we need. The label quality differs between different label sets. And the label themselves, they have real problems. Pedestrians versus riders, that might work, but traffic signs versus other signs and versus buildings is a big problem. You have to distinguish between cars, vans, and trucks, where you draw the line between these objects. Building and wall, we have seen in our data. Parking versus road, I will show you. Fences or poles. We have objects that you have never seen before, so the open world problem. And even if you have a very precise label definition, wall or building, your labeler will disagree. So we need a very exhaustive label quality control process, and labeling gets really expensive. And just think for yourself for a moment, what is a car? What is car, what is not car? Okay, I have some alternatives, something to offer here. All these objects have 4 wheels. Most of them have a steering wheel. That is what my 2-year-old boy told me 28 years ago. What the car is, it has a steering wheel and 4 wheels and headlights. Okay, he doesn't have headlights. What is a car, what not? I don't know. Trucks is a horror for me. You can put everything onto a trailer. Everything. And how to label that? Yeah, you see all the different toilets, tank, houses, whatever you like, you can put on a truck. Okay, how to label that? Not an easy problem. So if you take part in a benchmark, you take the definition as it is. But in practice, we have real problem. And I didn't expect how many days we discuss how to label what and how to label it consistently, so that in a year we will still be happy with our decisions. Because if we are wrong today, it's very, very expensive to go through all the label data and correct the labels according to a new label definition. Label noise, we have seen with the wall and the building, a simple image. And the labeler did a very good job. He precisely labeled here the street. But the neural network gives us this. Because most of the data, most of the labeler did it right. They said this is a parking area, and I labeled it as ground, not street. So the labeler was correct, and the ground truth is wrong, the result is correct. And if I take the same image on the other side, we also wanted the labeler to call this a ground, because this is also parking area. The networks are right. That labeler was consistent in his labeling. And we see that if we have a look to the loss function that we have here. Okay, we have a strong loss. To look for images where we have label inconsistencies or label noise. And the worst image is this one. Original output looks nice, doesn't it? However, that is a loss function. Right means wrong. Why? Because the labeler said, yeah, this is a correct labeling. Okay, the network says ground, not road. This is definitely wrong, but it hasn't seen much cobblestones before. Cobblestones are more like a sidewalk. Well, the labeler said, oh, I can't see the wall. Okay, network said, okay, everything is bushes. The fence here, usually we label just fence. This labeler labeled poles very precisely. Okay, and also here we say ground truth is wall, it comes also as building. So much label noise. And this is daily problem. I don't have answers for that. We use different methods to find the label noise, to reduce the label noise, hoping that it will help us in the classification. A totally other problem which we are concerned with is lost cargo, anything which is on the road. And you can't classify it as a specific object because anything can lie on the road. And we have to react to even small objects, heights of 12 centimeters, some wooden piece of wood can damage your car if you go over it too fast. So we have to look for systems that can, even at large distances, detect obstacles, small obstacles. And what we did is, Sebastian trained a neural network to recognize the street and the lost cargo, in this case, my 29 euro dog I bought from Amazon. Yeah, it's something that should not be there on the road. And also Ben, Marcus, 2-year-old boy, should not be on the road. And then my guys gave me that image. I was expecting that it reacts to all this painting. It doesn't, but where is the obstacle? I couldn't see. I asked the neural network there, and it's here, this wooden pallet. So we trained a classifier that can detect obstacles on the road, even we have no idea what it is, just by there's something that should not be on the street. And then we did a test. We put boxes, our animals here, everything here, and we drove over. And this is real-time reconstruction. It doesn't matter if we have an obstacle here at the side, so we will not drive into, but we get quite good and stable results. So this is not a real error for us. And you see, we drove on. We came back, but we had to wait because there was a garbage truck in front of us. And when we returned, an old mama, or old woman, had taken away all our obstacles because she thought the garbage truck had lost that pieces. Again, does it work at night? It should be robust. Okay, we trained at night a little bit, but not with that image. You see here 2 garbage bags. Yeah, there are 3. We look back. That's right. It's hard to see, but that should not be on the street. Yeah, robustness. Coming to the end. I'm happy with the Wilddash data set. That is a data set we need. Yeah, it's part of this workshop here. And I just took 6 images from the Wilddash data set. I added 2 images from my own data set. Here you see we have designers in Germany that are able to design wonderful bridges. No, that is just the Viper, which is curved due to the rolling shutter, which has 2 colors here due to the HDR effect. And it's correctly classified as bridge and building. Wonderful. Okay. Vipers are a real problem because at rainy days, and you want to do autonomous driving at rainy days, they're always in front of you. And we have seen that for stereo vision, it comes again. And I asked Jonas, co-author of this workshop, to render me an image. This is Frankfurt, and I asked him to make it brighter and brighter and brighter, and just to see what happens. It takes a long time, because we also do in data augmentation, but then if it gets too bright, it starts, the errors occur, it gets worse and worse and worse. And interestingly, if it's dark, if it's bright, 100% bright, we get that. And now I make it darker and darker. Okay, oops, even darker. Oops, okay. Bushes, forests, driving in the wild, and then we start making it brighter again and coming back. So what I wanted to show is, that surprised me. Oops, that is definitely not robust. Just by changing the mean of the image, we get different reconstructions. Maybe that is a consequence of our network, but this is far from being robust. So coming to the end, robustness in the wild is a major concern. We have all these different weather and lightning and open world challenges. But from a scientific point of view, and sometimes I have that in my heart, the problem is that we do not have a easy and generally acceptable definition or metrics for that. And if I'm a scientist, I'm always looking for the best average performance. And let's imagine you have an algorithm, this red one here, and this is the performance distribution over your data set. And you see the mean is here. You're happy because that is the award-winning algorithm. But then there's a second one that has a green distribution. And believe me, I would select the green one, because I'm mostly afraid of this portion here. So in practice, I'm looking for the least worst performance. And so we need a measure for robustness. Maybe if we are not able to come to a real robust system, then we need, from a practical point of view, we need to know when the system degrades or when it is not able to make a decision. So therefore, my personal belief is confidence measures will be the next big thing if you want to build up a complete vision system. And for the last slides, I love taking pictures of scarce objects and check what's going on with my network. This is the interpretation of that scene. Great. Here we don't have in the data set something like a bike with this box here. It's interesting to see what comes out. Great. Bike, part of car, pedestrian, rider. Great. Okay, wheelchair. It comes out, rider with a bike. I can accept that. I was interested in what happens here. Here, pedestrians, bus, truck, pedestrian. What happens here? Lucky, it's a truck. Okay, another truck. The lower part is truck, but this is grass, sky, trees. Great. Paintings. He's sitting here, people. Okay, pedestrian. We don't have a concept for horses, for animals yet. What happens? Here are animals. What do you guess? What the image what the scene labeling will tell us? Well, legs, body, head. Right, person. Last slide. You. What should come out here? The result is wonderful. Truck with a building and traffic signs. Okay, and I love to close my presentations by an image of the city where the conference takes place, and this is wonderful Salt Lake City. And here, usually I select the best image. This time I selected the worst one. Yeah, it seemed that we need more data, we need to learn this domain. Cityscapes is not taken in the Alps, it's taken in Germany, so we have no concept for all these mountains, except here are some people hiking, yeah, pedestrians over there. So let's finish my talk, and I conclude that the finding for robustness will continue. We will have workshops like this in 10 years, and this is the advertisement part. Everybody is hiring. Thank you very much. Questions?
I have two questions. The first one is that...
If you go forward to the mic.
Okay.
So the first question is that in the applications of ADAS and autonomous driving, usually we are looking for the bounding box representation for objects like vehicles, pedestrians. So, but here in your talk you mentioned the instance-based segmentation. So, what can instance-based segmentation? What are the additional benefits that instance-based segmentation can bring to the application, such as ADAS and autonomous driving, in addition to the bounding box detection?
Well, we have imagine a group of people. We have a much more precise interpretation of the situation. We can better concentrate on different people, what they are doing. We we can do 2D boxes, we can do 3D boxes, but we believe that it might be beneficial if we have precise instance segmentation. And I didn't talk about box detection today because it's not a part of the Cityscapes benchmark. It's part of Kitty benchmark. And I thought it's of interest to you if I show you some images from Cityscapes you haven't seen before.
Okay. My second question is that I know that the Daimler has done a lot of stereo matching. Has done a lot of research on the stereo matching, but on the other hand, for example, the Mobileye seems never been a fan of a stereo-based solution, and also like our next topic is also trying to estimate the depths based on single image. So, what's your comments on the stereo-based approach, and how do you think about the future of stereo-based approach?
That is the old and always ongoing discussion between Mobileye, Shashu, and me. We found that we are significantly faster in reaction to dangerous situations, the child running onto the street, all the situations, because we have the 3D information directly. It's easier to fuse with radar and LiDAR, because also vision has a precise depth. Of course, you can do depth from mono, but then you have a problem if you see objects we have never seen before, because if you do depth from mono, you learn the scene, you learn objects, you have a clear image of the size of cars, and if that is wrong for any reason, you saw the train in my pictures over there, then those algorithms might fail. It's an ongoing race. We think at Daimler that we do better with stereo. We have the technology. It's in all our cars. So why not use it? Mobile doesn't have the technology. You need online calibration. You need everything to make it robust. And they all the time stayed with mono. But we have the technology, so it's not a big deal for us to use it.
Thank you.
I think we have to close.
Yes. Probably one more last question. Yes.
Thank you for the wonderful talk. The video you showed at the end where you increased the brightness level and made it dark was great to see. I was actually already wondering during your talk whether you and your team looked at these kind of adversarial attacks that are being applied to DNNs to change their predictions completely. Now for these labeling tasks, have you seen similar behaviors? Like if people are injecting other kinds of noise into the images, can they perturb these predictions in a bad way? Do you have any thoughts?
We look for adversarial attacks, of course. I'm optimistic. I prepared slides for that, but for the lack of time, I can't show. I'm optimistic that the problem is not as big as we make it here, because it's scientifically a very nice problem, but also the old classifiers could be fooled by many different things. Right. So I hope that we can bring it back to a situation that we had 2013. Our pedestrian recognition system, our emergency braking system is a classifier. And nobody talked about adversarial detects that time. Right. We have to find a way.
Right. But so you believe that these CNN seem to be somehow more robust, like these kind of labeling, FCN
I don't
or
know.
that family?
I make no comment on that.
Okay.
I didn't compare that.
Okay. Thank you.
Right. Let's send this speaker again.